Welcome to another episode of Breaking Math, where we take a deep dive into how mathematics shapes our understanding of the world. I'm your host, Autumn Finef. Today, we'll be exploring a topic that at first glance may seem simple, but quickly reveals its unexpected complexity: the movement of sheep. Yes, that's right, sheep. Those fluffy, gentle animals often seen wandering in herds. But what if I told you that their movement as a group can be explained using the same mathematical principles that have described how fluids flow? You might think of fluid dynamics as something that applies to rivers, ocean currents, or the airflow over airplane wings. But these principles also govern how groups of animals like sheep, birds, or fish move together in coordinated patterns. This episode will show you how such groups of behavior can be studied through the lens of mathematics, specifically through the framework of fluid dynamics. You see, when animals move together in large groups, whether on land or in water, they often behave like a fluid, flowing smoothly around obstacles, maintaining distance from each other, and sticking together as a unit. This is what makes the study of collective animal behavior so intriguing. By examining how animals like sheep move, we can uncover underlying mathematical patterns that govern not just animal herds, but many other systems in nature and society. In this episode, we'll explore how sheep herd behavior is modeled using principles of fluid dynamics. We'll start to break down what fluid dynamics is and how it applies to both liquids and gases. Then we'll dive into how the same mathematical framework can be used to understand the movement of sheep and herds. We'll also explore some fascinating mathematical models like the Boyd model that simulate how animals behave in groups. And finally, we'll discuss the practical applications of these models, from improving livestock management to designing more efficient traffic systems and even programming autonomous drones. So, whether you're a math enthusiast, biology buff, or just someone curious about how something as ordinary as sheep can reveal hidden mathematical beauty, stay tuned. We're about to uncover the fascinating connections between mathematics, nature, and behavior. To fully appreciate how sheep behavior relates to fluid dynamics, it's important to first understand what fluid dynamics actually is. In essence, fluid dynamics is a branch of physics and mathematics that deals with how liquids and gases move. These substances, collectively referred to as fluids, don't behave like rigid objects. They flow, they swirl, and they change shape depending on the forces acting on them, like gravity, pressure, and even temperature. The basic tools for studying fluid dynamics are the Navier-Stokes equations, a set of differential equations that describe the motion of fluid substances. These equations explain how velocity, pressure, density, and other properties evolve in a moving fluid. When we think of fluid dynamics, we might imagine water flowing in a river or air moving over a car's surface to reduce drag. But what's remarkable is that these same equations can be applied to seemingly unrelated systems, like the movement of animals in groups or even the flow of cars on a highway. So, how does this relate to sheep? Well, while sheep are certainly not liquids, when you zoom out and observe a herd from a distance, the movement of a group begins to resemble the flow of a fluid. This is where things get interesting. In a fluid, each particle has its own velocity and is influenced by the particles around it, creating a dynamic, constantly shifting system. Similarly, in a herd of sheep, each animal moves independently, but in response to the sheep near it, creating an overall movement that looks surprisingly fluid. In fluids, there are two primary types of flow: laminar and turbulent. Laminar flow is smooth, orderly, and predictable, while turbulent flow is chaotic and full of swirls and eddies. What's fascinating is that sheep herds exhibit both types of movement depending on their state. When calm, the move is laminar, smooth fashion. But when startled, their movement becomes turbulent and chaotic as they are scattered unpredictably. These behaviors can be modeled mathematically, revealing deep insights into both animal and fluid behavior. In addition to these physical parallels, there's another concept in fluid dynamics called active matter. Active matter refers to systems made up of individual units, like animals, bacteria, or even robots, that consume energy to move and interact. Unlike passive particles in a fluid, active matter systems are driven by internal forces, biological, social, or mechanical, that influence movement. Sheep in a herd are a perfect example of active matter. They follow simple internal rules based on how their instincts and their interactions with neighbors. They follow simple internal rules based on their instincts and their interactions with their neighbors. These rules, when combined, lead to complex emergent behavior that resembles the flow of a fluid. So, how exactly do sheep behave like particles in a fluid? When we model sheep herds mathematically, we treat each individual sheep as if it were a particle moving in response to its neighbors, much like how molecules in a liquid move in response to pressure or velocity changes. These individual sheep interact with each other based on three key behaviors: alignment, cohesion, and separation. First, alignment refers to the tendency of each sheep to follow the general direction of the herd. If most of the sheep are moving in a certain direction, the others will adjust their course to match. This keeps the group moving together in the same direction and prevents the herd from splitting apart. It's similar to how particles in a fluid align with the overall flow. Cohesion, the second behavior, describes the natural inclination for sheep to stay close to one another. Sheep are social animals, and they feel safer when they're part of a group. Just like particles in a fluid tend to cluster together, sheep move towards the center of the herd when they feel they are drifting too far away. This ensures the herd remains a cohesive unit and doesn't break apart into isolated individuals. Finally, there's separation. While sheep want to stay close to each other, they also need to maintain comfortable personal space to avoid collisions. If two sheep get too close, they'll instinctively move apart to avoid bumping into one another. In fluid dynamics, a similar phenomenon occurs when particles repel each other to maintain an optimal distance. In fluid dynamics, a similar phenomenon occurs when particles repel each other to maintain an optimal distance. When you combine these three simple behaviors, alignment, cohesion, and separation, the result is an emergent phenomenon where the group moves fluidly across the landscape. No single sheep is in charge of directing the herd, but their individual actions create a coordinated collective behavior that seems almost orchestrated. This is a concept called self-organization, where complex patterns arise from simple local interactions without the need for central control. Mathematically, we can describe this group movement using velocity fields, which show how fast the sheep are moving and in which direction. These velocity fields are similar to those used in traditional fluid dynamics to describe how liquids or gases flow. By tracking the movement of each sheep in the herd, scientists can create mathematical models that predict how the group will respond to changes in the environment, like an approaching predator or sudden obstacle. Now that we've explored how sheep behavior resembles fluid dynamics, let's take a deeper look at the mathematical models used to simulate these movements. One of the most influential models for studying group behavior is the Boyd model, developed by computer scientist Craig Reynolds in 1986. Originally designed to simulate flocking birds, the Boyd model applies equally well to other animals, including sheep. The Boyd model is based on the same three behaviors we just discussed: alignment, cohesion, and separation. Each Boyd, a simplified bird-like agent, follows these rules in relation to its neighbors, creating realistic, lifelike group behavior. This model doesn't require any central control. Instead, the movement of the group emerges from local interactions between individuals. In the context of sheep, each animal is treated as a Boyd, and the model simulates how the herd moves as a cohesive unit. What's remarkable about the Boyd model is its simplicity. Despite being based on just a few rules, it produces incredibly complex and realistic behavior when applied to large groups. For example, the Boyd model can simulate how a herd of sheep avoids obstacles, adjusts its shape to fit through narrow spaces, and even splits and reforms under certain conditions, just like a real herd of animals would in the wild. In addition to the Boyd model, other mathematical frameworks are used to study collective behavior. One such framework is the cellular automation model, which divides space into a grid of cells. Each cell can either be occupied by a sheep or empty. and sheep move from cell to cell according to simple rules. This model is particularly useful for simulating situations where space is limited, such as herds moving through narrow passages. Another important model is the continuum model, which treats the herd as a continuous mass, much like fluid. This approach is closer to traditional fluid dynamics, as it's particularly useful when studying large herds where the individual behavior of sheep becomes less important than the overall flow of the group. In a continuum model, the movement of the herd is described by using equations that account for density, velocity, and pressure, just like the equations used to describe the flow of water or air. Both the Boyd model and continuum model have their strengths. The Boyd model captures the local interactions between individual sheep, while the continuum model excels at simulating large-scale behavior. In recent years, researchers have developed a hybrid model that combine the best of both approaches. These models treat the herd as a fluid at a large scale, but zoom in on the individual sheep and capture their local interactions. This allows for a more accurate simulation of the herd under different conditions. The study of fluid dynamics in animal behavior isn't just theoretical. It has practical applications in a wide range of fields. For instance, understanding how sheep move can improve livestock management. Farmers have long known that sheep tend to move together in predictable ways, but by applying mathematical models, they can better control the flow of animals during herding, reduce stress on livestock, and improve overall efficiency. Drones or trained sheepdogs can be used to guide the herds in ways that align with their natural behavior rather than trying to control individual animals. Fluid dynamic models also help in the design of more efficient systems for crowd management. Whether it's people moving through a busy city square, fans exiting a stadium, or cars on the highway, these models allow us to predict how individuals will move in groups. For example, by treating cars on the highway as particles in a fluid, researchers can develop systems that reduce traffic congestion and prevent bottlenecks. Another exciting application is in the field of robotics, where swarming robots are designed to mimic the movement of animals like sheep. These robots follow simple rules similar to those of alignment, cohesion, and separation to move collectively and achieve goals. Swarming drones, for example, can be deployed in search and rescue missions or disaster response, where they need to navigate complex environments without central control. Each drone adjusts its flight path based on local information, just like sheep moving through a field. In autonomous vehicles, similar principles are being used to design systems that allow cars to move safely through traffic by communicating with one another and adjusting their speeds based on local conditions. This could lead to safer and more efficient traffic systems, reducing accidents and improving travel times. Fluid dynamics is even being applied to biology. Researchers are using these models to study how cells move and interact in living organisms, which has implications for understanding wound healing, tissue regeneration, and immune responses. Just like sheep in a herd, cells in our bodies respond to external signals and move in coordinating ways to achieve complex tasks. As we've explored today, the movement of sheep in a herd is a surprisingly complex and elegant process governed by simple rules that can be described using the mathematics of fluid dynamics. These rules, alignment, cohesion, and separation, lead to emergent behavior that mirrors the flow of liquids and gases. What's even more fascinating is that the same mathematical principles used to describe water flowing around a rock or air moving over a wing can also explain the behavior of animal herds, traffic, crowds, and even robots. The study of collective behavior, whether in animals or artificial systems, has far-reaching applications in the fields ranging from agriculture and robotics to urban planning and autonomous vehicles. By understanding how simple rules can lead to complex, coordinated behavior, we gain new insights into the natural world and develop innovative solutions to real-world challenges. So, the next time you see a herd of sheep moving across a field, remember that you're witnessing a real-life demonstration of fluid dynamics in action. This seemingly ordinary process is a perfect example how mathematics helps us uncover patterns in the world around us. Thank you for joining us on this episode of Breaking Math, and I hope you enjoyed this exploration of the fluid dynamics of sheep And I look forward to having you with us next time as we continue to explore the fascinating connections between mathematics and nature.